Hey there, and welcome. Today, we're jumping into vector arithmetic. Seriously, whether you're in pre-calculus, taking a physics class, or you just think math is cool, getting a handle on vectors is a total game changer. It's the language we use to talk about forces, velocities, and a whole lot more.
I mean, think about it for a second. An airplane has its engines pushing it forward, its wings giving it lift, gravity pulling it down, and the wind blowing it sideways. So how in the world do we figure out where it's actually going? Well, the answer is vector arithmetic. It's how we take all those invisible pushes and pulls and combine them into one single predictable path.
All right, so let's build our vector toolkit. We're going to start with the three core operations: adding vectors, subtracting them, and then scaling them up or down using something called scalar multiplication.
Vector addition is, you'll be happy to hear, as straightforward as it gets. You literally just add the matching pieces together. Add the x values to get your new x value, and add the y values for your new y value. That new vector you get, that's their combined effect. Simple as that.
Now, the formula's great, but seeing it is what makes it click. The head-to-tail method is kind of like following a map. You walk along the path of the first vector, and right where you stop, you start walking along the path of the second one. The final answer is just a straight line from where you started to where you ended up. The parallelogram law gives you the exact same result, but it shows us something really powerful. That diagonal cutting across the middle, that's the net force, the single vector that does the job of the other two combined.
Next up is scalar multiplication. And please, don't let the name intimidate you. A scalar is just a fancy word for a plain old number, like 2, or -10, or even 1/2. When you multiply a vector by a scalar, you just pass that number out to each part of the vector. That's it.
So what does this actually do to the arrow? Well, if you multiply by a number bigger than 1, you stretch the vector out. If you use a fraction between 0 and 1, you shrink it. And here's the really cool part. If you multiply by a negative number, it completely flips the vector's direction, making it point exactly the opposite way. So you can change its size and reverse it. And that brings us perfectly to subtraction. You see, the easiest way to think about subtracting a vector is to just think of it as adding the opposite. So to get u minus v, you just take vector v, flip its direction around, and then add it to u using that head-to-tail method we just talked about. See? It turns a new operation into one we already know how to do.
Okay, enough with the theory. Let's put this stuff into practice. We're going to walk through a couple of examples right now to really make these ideas stick.
Okay, here's our first one. We've got two vectors, u and v, and we just need to find their sum. Feel free to hit pause and try it on your own before we solve it together. All right, let's see how you did. First, we add the x components. 4 plus -1 is 3. Then we add the y components. -2 plus 5 is also 3. So the final resultant vector is just 3, 3. See? Not too bad, right? Now for something a little more fun. This is what we call a linear combination. This problem mixes everything together, scalar multiplication and subtraction. This is a super common type of vector problem. So let's break it down piece by piece. We're going to do this step by step. First up, let's figure out 2 times u. That's just 2 multiplied by each component, which gives us the vector 2, 8. Easy enough. Next, let's get 3 times v. Again, multiply it out, and we get 6, -3. Now for the last step, we subtract that second result from the first one. For the x part, 2 minus 6 is -4. And careful here, for the y part, we have 8 minus a -3, which becomes 8 plus 3. That gives us 11. So our final answer is -4, 11. Okay, this next part is super important. Let's talk about how to avoid the common traps. Paying attention for the next minute or two can save you a ton of points on a test.
This is, without a doubt, the biggest mistake students make. The length of the sum of two vectors is not the sum of their lengths. Let me say that again, you can't just add their lengths together. The only correct way to do it is to add the vectors component by component first. Get your new result vector, and then you can calculate the magnitude of that final vector. And here are 2 other little traps. First, watch your signs when you subtract, especially if you're subtracting a negative number. It's such a classic algebra mistake, and it's so easy to make when you're in a hurry. Second, always remember to distribute a scalar to every part of the vector, not just the first one.
So why do we even bother with all these arrows and numbers? Well, in this last section, we're going to see exactly how important this stuff is in the real world. One of the biggest applications is in physics, with this idea of equilibrium. If an object isn't moving, it means all the forces acting on it, gravity, tension, you name it, are perfectly balanced. When you add all those force vectors up, they have to equal the zero vector, 0, 0. They completely cancel each other out.
And this isn't just theory. The stakes are massive. Engineers do these exact calculations to make sure a bridge can handle the weight of cars, the force of strong winds, and its own weight all at once. Vector arithmetic is literally what keeps our buildings and bridges standing strong.
So, I'll leave you with this little challenge. Start looking for the vectors in the world around you. From the path of a ball you toss to a friend, to the way the wind pushes you on a bike, they are absolutely everywhere, just waiting for you to add them up. Thanks for joining me.